Alright, here we go with the Chapter 2 Homework 1 review. We're going to be covering a few problems where the scores on these were a little bit lower than some of the rest, and sort of trying to shore up some of the concepts that we may have glossed over in lecture and give you some problem-solving strategies for how to deal with these on future assignments. Alright, so I picked out about 6 questions or so that I'll go through, and as usual in the future, if you have any specific questions you want me to cover, please let me know and I'll include those in future iterations of this video. Alright, so we're going to start with a couple questions about the Bohr model. Alright, so the Bohr model is the idea, this very simplified idea of atomic structure that electrons move in circular orbits around the nucleus, and the energy of those electrons has a very well-defined value and a very simple equation to describe it. And very often in these questions, as we'll see, you're going to be asked for something about the wavelength or frequency of light that is involved when an electron moves between these energy levels. So when an electron does move either to higher energy or lower energy, a photon is either absorbed or emitted, and we can use this Bohr equation to indirectly tell us about the wavelength or the frequency of that photon. But the Bohr equation won't give us that directly. We need to convert into wavelength or frequency, as we'll see. So in this question we're asking, what is the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from n equals 5 to n equals 3? So there's a fairly simple equation, the Bohr equation, that gives us the change in energy when an electron moves between two energy levels. So the constant that goes out front is minus 2.18 times 10 to the minus 18 joules. And then you're going to have 1 over nf squared minus 1 over ni squared, where these are the two values of n that the electron is moving between. And if we care about the sign of delta E, which in this question is not so important, but in other questions we may want the sign, we need to have NF is the final n value, that's where the electron ends up, Ni is where the electron started. So in this question, if we want to be rigorous about the different n values, we're going from n equals 5, so that's our initial value of n, to n equals 3, that's our final value of n. So the first thing we're going to do is we're just going to use this equation with these two values of n. So the final value of n is 3, the initial value is 5, and so when we put these out in the calculator, we get a delta E of minus 1.55 times 10 to the minus 19 joules. So that's the energy change of the electron as it moves from n equals 5 to n equals 3. It's going from a higher value to a lower value, so delta E is negative. And then remember that there's going to be a photon involved in this. In this case, it's going to be a photon that's emitted because the electron is losing energy. And so the energy of the photon is just equal to the absolute value of delta E. So the photon energy is going to be just 1.55 times 10 to the minus 19 joules. We never have negative photon energies or wavelengths or frequencies. So, but remember that this is the energy of the photon, and this question specifically wants the wavelength of light. So many of you picked choice C here. This is the energy, and that's the most common incorrect answer was choice C. So you did the calculation right, but you have to realize that this number does not represent the wavelength of the photon, it represents the energy. Alright, so that's not the correct answer. We have to do one more step, and remember that the energy of a photon is equal to h times the frequency, which is equal to hc over lambda. So lambda is the wavelength, that's what we're interested in. And so if we solve for lambda, it's going to be hc over the energy of the photon. And so h is 6.626 times 10 to the minus 34. C is 3 times 10 to the 8th. And the energy of the photon that we just solved for is 1.55 times 10 to the minus 19 joules. And we'll have to work backwards here, so I'm running out of room. So putting the answer above there, I got 1.28 times 10 to the minus 6. That's exactly one of our answer choices. Alright, so this is going to be the wavelength of the photon that's involved, and that corresponds to choice B. Alright, so whenever you use the Bohr equation, make sure you don't stop too early. Go to the end and find out what exact value are you interested in this case is wavelength. And so this problem then is very similar. What is the frequency of radiation when an electron falls from the n equals 4 to n equals 2 level of the hydrogen atom? And so again here we're talking about two different values of n. This is our final value, sorry, this is our initial value, heading backwards. This is our final value, nf. And we're just going to use the Bohr equation to find the change in energy first. Alright, so the final value of n is 2, the initial value is 4. Alright, so exact same setup as the last problem, just different numbers. So I got 4.09 times 10 to the minus 19 joules. This should be a negative number again. Alright, so again, that's the energy change from n equals 4 to n equals 2. And then the energy of the photon is equal to the absolute value of delta E, which is just going to be positive 4.09. Alright, so again, many of you picked choice E. This is the energy of the photon, but we're interested in the frequency in this case. So here the math is even a little bit simpler. So the energy of the photon is equal to just h times the frequency, so that means the frequency is just equal to the energy divided by h. This is going to be 4.09 times 10 to the minus 19 joules divided by 6.626 times 10 to the minus 34 joule seconds. That's Planck's constant h. And so when we divide these out, we get 6.17 times 10 to the 14th seconds to the minus 1, which is equivalent to 6.17 times 10 to the 14th hertz. So hertz and inverse seconds are the exact same unit. So this asks for hertz, so you don't have to do any conversion here. So choice A is going to be correct. Now another persistent difficulty on these problems, many of you are having a little bit of trouble with the exponent function on your calculator. I know it sounds like a silly thing, but every calculator is a little bit different. So if you're using a new calculator, or if you're using a scientific calculator when you're used to a graphic calculator, make sure you know the proper syntax for doing exponential operations, because we're going to be using those a lot, especially in this section of the course where we have to use the speed of light, which is 3 times 10 to the 8th, and Planck's constant, which is 6.6 times 10 to the minus 34. So become familiar with that, and make sure that that doesn't become something that holds you back on these types of problems. Alright, so that takes care of the Bohr model, and the rest of the questions that I'll go over have to deal with the quantum mechanical model and, to some extent, and then electron configurations. So this question here, multiple choice question, in some sense is a little bit of a trick question. It really tests your understanding of these quantum numbers. How many electrons can be described by quantum numbers n equals 3, L equals 3, m sub L equals minus 1? Now if these were a valid set of quantum numbers, there would only be a maximum of 2 electrons that could be described by that. That's what Pauli exclusion tells us. But we first have to check to make sure if this is a valid set of quantum numbers. So n equals 3 is a valid for the first quantum number, so because n can be 1, 2, 3, 4, and so on. So n equals 3 is an okay quantum number for the first quantum number, the principal quantum number. But then the values of L and m sub L that are allowed are going to depend on the value of n. So if n equals 3, L can have the possible values from 0 all the way to n minus 1. So in this case, the possible values of L are 0, 1, and 2. So if n equals 3, L cannot also be 3. Okay, so that's an invalid quantum number for L, which means there are no electrons that can have this set of quantum numbers. So the correct answer is A. We don't even need to look at the m sub L value and whether that's going to work out, because the value of L is just not a valid one we can use. So always check when we're doing these kinds of problems to make sure that the quantum number relationships, the hierarchies that we talked about in class, are followed. And in this case, the value of L that we have is not one that works out. Alright, moving on to some problems dealing with electron configurations. So this one, which of the following have 10 electrons in the d orbitals? So we have 4 choices, 4 different elements, and then one of them, the answer choices is 2 of these. So really what we have to do is write out the electron configuration for all of these, and this will be a good chance to review and practice electron configurations as well. Alright, so we'll start with iron, Fe. We go to the periodic table, so we need to find these on the periodic table, and that's going to then help us determine the configuration. So Fe is right here, atomic number 26. So if we go through the electron configuration, remember the shorthand method goes back to the previous noble gas, and especially since these are all 3d metals, we're not going to have any d electrons that occur before this, so we're asking a question about d electrons. We don't need to consider all of the core electrons. You know, the full configuration would have 1s2, 2s2, 2p6, and so on, but we can write the noble gas configuration to abbreviate all the core electrons. So argon is the noble gas that precedes all of these elements. So our shorthand notation is going to have argon in brackets. That means we have all of the electrons from argon, and then we're going to add in the valence electrons beyond there. So we go to argon, the next row of the periodic table. This is the 4th row, and this is the s block, so we have 4s2. And then to get to Fe, we have 3d, 1, 2, 3, 4, 5, 6. So we're going to have argon, 4s2, 3d6. The question asks which of these have 10 electrons in the d orbitals. This one clearly is not one of them, so we're not going to count that. The next one is copper. So copper is very close to iron in the periodic table. And remember that copper is one of our exceptions. So for copper, we would predict, again, argon is the previous noble gas. We look at copper, and it's going to be 4s1, 2, and then 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9. We predict 4s2, 3d9, but remember that that's not the correct configuration for copper. It's actually going to be argon 4s1, 3d10. So this is a case where we promote one of the electrons from 4s into 3d. Still the same total number of electrons, but we've moved one from the 4s into the 3d. Okay, so this one does have 10 valence electrons, or sorry, 10 d electrons, so that's one of our choices. And then zinc is going to be the next one we go through. So zinc is over here right next to copper. So if we go through zinc, it's going to be argon, and it's going to be 4s1, 2, 3d, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alright, so this just has one more electron than copper, giving a configuration of argon 4s2, 3d10. So in this case, both the 4s and the 3d subshells are filled, and again we have 10d electrons. So now we have 2 answer choices that work, so that should hopefully mean that D is the correct answer. We can verify manganese and see how many d electrons this has. Alright, so again, argon is a preceding noble gas. When we go to manganese, it's going to be 4s2, 3d, 1, 2, 3, 4, 5. Alright, so manganese also does not have 10 d electrons, it only has 5. Okay, so that's going to give answer D. 2 of those will have 10 d electrons. Alright, so these give us some good examples of electron configurations for transition metals. And remember that for transition metals, we have to fill 4s before 3d, and in the cases of chromium, which wasn't on here, and copper, which is on here, we have to remember these exceptions where we promote one of the 4s into the 3d to give a slightly different configuration. Alright, so that's one question that had to deal with configurations. Now we have 2 others here. So we have 2 problems of this type that I want to go over. Some of you missed these ones because you didn't format your answer correctly. For those of you that were just missing a space in between the 2 terms, we wanted you to put a space between the symbol and the number of electrons. If that was the case, I gave you the point, but please follow the directions carefully in the future. But many of you missed this for other reasons as well, so I do still want to go over it. So we're giving you the electron configuration for a neutral atom. We want to identify the element and state the number of unpaired electrons in its ground state. So for identifying the element, we could kind of work backwards what we did before. We could go to the periodic table and find, where are we in the periodic table when we're at the neon 3s2, 3p5 configuration. That will certainly work, but if all we're asking you to do is identify the element, which is half of this question anyway, all you really need to do is just count the total number of electrons. Alright, so the total electrons, if we have a neon 3s2, 3p5 configuration. So we go to the periodic table. Neon are the core electrons. So neon is atomic number 10. So there's going to be 10 core electrons. And then we have 2 electrons from the s subshell, 5 from the p. And so whatever element this is going to have 17 total electrons. Alright, so this is the correct configuration, but we don't really need to know the exact configuration to identify the element. We just need to know how many electrons there are, which for a neutral atom is going to also be the value of Z. So the atomic number for this unknown element is 17. We go to the periodic table, and that's right here, chlorine. Okay, so chlorine is the unknown element, but now we want to ask how many unpaired electrons are there in this ground state. And even the electron configuration by itself, which we're giving you, is not enough to know how many electrons are unpaired. For that, you really need to write out the partial orbital diagram, at least for the valence electrons. So if we have a 3s2 configuration, remember there's going to be one 3s orbital, and then for the 3p subshell, we have 3 degenerate p orbitals with the m sub l values -1, 0, and +1 for 3p. So these are the available valence orbitals, and we're going to follow Hund's rule to fill these up and figure out how many electrons are unpaired. So we have 3s2, we're going to have 2 paired electrons in the 3s, so there's going to be no unpaired electrons there. And if you go to 3p5, we have 1, 2, 3, 4, 5. That leaves us with, right here, 1 unpaired electron. So remember, an unpaired electron is one that has a certain spin value without another electron of the opposite spin paired with it. Okay, so we have these two are paired, spin up, spin down, spin up, spin down, but then in this p orbital here we have 1 unpaired electron. So the correct answer then would be Cl, space 1, if you want to format it correctly. So the element is chlorine, and we just wanted the symbol, and then we have 1 unpaired electron. Alright, and then this question is almost identical. We're giving you the configuration, identifying the element. Now we've actually seen this one on a previous problem, argon 4s1 3d10, but again, if we hadn't seen it before, we didn't realize this, we can still just look at the total number of electrons to identify what the element is. So for the argon, 4s1 3d10 configuration, we look at the number of electrons in there. And so argon are the core electrons. That's going to be atomic number of 18, so there's going to be 18 core electrons. We have 1 electron in the 4s, 10 electrons in the 3d. So it's going to be a total of 18 plus 1 plus 10 is 29 electrons, and so the atomic number is going to be 29 for this neutral element. We go to the periodic table, and that's copper, atomic number 29. Alright, we saw the configuration of copper earlier. It's one of those exceptions. But so now we know we have identified the element, but we still have to go through and figure out how many unpaired electrons there are. So we have the 4s subshell, and then remember for 3d, we have L equals 2, M sub L is equal to -2 all the way to +2. So there's going to be a total of 5 3d orbitals. And we know that in a 3d subshell there's a maximum of 10 electrons, which means there's 5 orbitals. So if we're going to have 5 degenerate 3d orbitals that we're also going to populate with electrons. So this configuration, again with that exception of moving one of the s electrons up, is going to be 4s1 3d10. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all of the d electrons are paired, and many of you put 0 as part of your answer, saying that there were 0 unpaired electrons, but we can't forget about this 4s. Even though it's not the last subshell that we filled, it does have 1 unpaired electron in it. So it's going to be copper with also one unpaired electron. Alright, so most of you identified the element correctly on this problem, but many of you had the wrong number of unpaired electrons. And so when we want to know the number of unpaired electrons, we need to write out the partial orbital diagram, use Hund's rule to fill them with electrons, where again we go 1 electron per orbital, all with the same spin, then we pair them up, and whatever we're left with, we know how many unpaired electrons there are. Alright, so that takes us to the end of this review. We'll have another homework on this chapter next week, so you get a more of a chance to review a lot of these same topics and some of the related things that we talked about at the end of class. So we'll come back next week and go over whatever additional problems we have on that assignment. All right, I will see you next week with the next homework review.